Hi, welcome to this section of the Probability and Statistics Tutor, and in this section we're going to cover the topic of Bayes' theorem. Okay, so Bayes' theorem is really nothing more than an extension of what we did in the last section. So if you haven't watched the last section, go ahead and do that right now. And the last section was on the topic of conditional probability. And just to remind you what that is you have two events, and what you're trying to do is you're trying to find the probability of that both events occur. And so what you're usually doing there, probability of A times probability of B given that A has occurred. So when you're finding the probability of B, you need to be taking into account that A has actually occurred, okay? So Bayes' theorem is just a theorem that kind of extends that. So it's exactly what we've been doing in the last section, but we're extending it to more complicated problems. The main difference between these problems and the problems in the last section is going to be that there's going to be more than one possible path to get to the second event that you're trying to look at, and we'll see why that is here in just a second. So just keep that in mind. It's the same thing that we've been doing last time, but it's kind of extending it to more complicated problems when you have multiple paths to get to that second event, multiple ways, I should say, to get to that second event, okay? The easiest way to do it, rather than do what most of the books do, most of the books will just put Bayes' theorem down on a sheet of paper and tell you to use it. I want to go ahead and do things a little bit differently and start with a problem and sort of hopefully explain to you as we go through this problem why Bayes' theorem makes total sense, so that you're not just memorizing something, you actually understand something. So here's the problem. It's fairly lengthy, and in fact all of these problems you will find are pretty lengthy with a lot of numbers in there, but the good news is once you understand the type of problems that Bayes' theorem is used to solve, you'll be able to tackle all of them because they pretty much all have the same form, okay? So here goes. Here's the problem. Suppose that three plants make cars, okay? So somebody's making automobiles, cars, and three different plants can make them. Plant B1, plant number one, B1 makes 60% of the cars. Plant B2 makes 30% of the cars. Plant B3 makes 10% of the cars, okay? Plant B3 makes 10% of the cars. Furthermore, 95% of the cars from plant B1 never fail, okay? And 80% of the cars from plant B2 never fail, and 65% of the cars from plant B3 never fail. So given all of that stuff, what we want to do is we want to find the probability that if I go out and buy a car that's produced by one of these plants, what is the probability that it's going to be error-free or never have any problems or never fail, okay? So one more time, let's run through it, because once you understand the form of these types of problems, they'll all look similar, okay? You have three plants. Plant B1 makes a certain percentage of the cars, plant B2 makes a certain percentage of the cars, plant B3 makes another percentage of the cars. Add all those percents up, they're always going to add to 100% because all the cars come from those three plants. So B1 makes 60%, B2 makes 30%, B3 makes 10%. Okay? Now furthermore, we know that plant B1 has error-free cars, or cars that never fail 95% of the time. Plant B2 has 80% of the cars never fail. Plant B3, 65% of the cars never fail. So what we need to do now to really make sense of this is draw a picture, and I'll think you see what's going on. So what we want to do, and by the way, you will do this for every single problem of this type. You're going to be drawing a picture like this, okay? So what we're doing is we're saying there's three plants, B1, B2, and B3. The idea here is here's a car, a little car is built, right? My terrible little car. That's supposed to be a car. A car is being built. It can only be built by one of three plants, and that's why the lines go off like that, because it has to go from one of those plants. Okay? Let me switch up the colors a little bit here, okay? We know that 60% of the cars come from B1, so you're going to have to convert that to kind of a probability, 0.60. Because, you know, we don't deal with percents and probability. We deal with decimals, 0.6, 0.5, 0.4, something like this, okay? 60% of the cars come from B1, okay? 30% of the cars come from B2, and 10% of the cars come from B3. So that covers all three possible paths from the manufacturer of this car. What percentage of the plants that produce a certain percentage of the car. So the car must be built by one of these three plants. This is what I was talking about earlier when I was saying that Bayes' theorem deals with problems that have multiple paths to get to the destination. Well, this is what I'm talking about. There's three different ways this car can be built by three different plants. Okay. Now, furthermore, we know that plant B1 has error-free cars 95% of the time. Okay? And what I'm going to do is I'm going to put a letter out here, A. Okay? You'll see why I'm going to do that in a second. B2, let me do it like this. Plant B2 and B3 also produce cars, each leading to event A. We'll get to that in a second. Plant B2 has error-free cars 80% of the time. And plant B3 has error-free cars 0.65, probability of 0.65. So everything in the problem was given in terms of percent, but I'm converting it to probabilities. So the car comes out, 60% is made by B1, 30% by B2, 10% by B3. Okay, now if the plant was actually built at B1, 95% of the cars are built. That's what the event A is. It's actually the problem-free cars that come out at the end. 80% of the cars come out are error-free here for B2, and 65%, basically 0.65 probability, come out being error-free over here. So knowing what this stuff is, what we're going to just go ahead and write down, event A is a car is error, or defect, I guess you could say, free. Okay? That's what that event is, okay? And then B1, B2, and B3 are also events, and this is just telling you what we already know, is like which plant builds the car. Okay, so I've got a complicated looking drawing here. Basically, there's 3 plants that build a car. Here are the probabilities the different plants have built the car, and of these cars that come out of these plant factories, certain percentages of them actually come out without any problems. Okay, so obviously B1 is the best plant available, but he doesn't make as many cars. And plant B2 is also a fairly good plant, and he doesn't make so many cars. Plant B3 is the worst producer of cars at all as far as the defects. It has the less perfect cars coming out, and he makes the least cars of everybody. Okay, so that's what we have so far. So the question is, if I buy a car, just any car, and I don't know where it's built, what is the probability that it's going to be defect-free or error-free? What's the probability I'm not going to have any problem with it? Well, you see, each individual path is telling me, if I go along this path, I'm basically going to know, here's the probability of B1, which is the car was built at B1. This is the probability of a defect-free car given that it was built by B1. That's what this line coming out of B1 is. This means the car was built with a 0.3 probability coming out of B2, and this probability means that it's defect-free given that it was built by B2. And the same thing here, 0.1 chance that it was actually built by B3, and then this number means that it's defect-free given that it was actually built by B3. So what we're basically going to have here, okay, what we want is the probability of A. That's what we want. We know the event A comes out of 3 different paths. That's what I was talking about. There's 3 different ways to get to event A. Event A is that my car is perfect. There's nothing wrong with it. I want to find the probability of event A, which is the probability that the car is fine. So what I'm going to have to do is I'm going to have to sum, that's what the sigma means, over all paths. Okay, so there's 3 ways to get to event A, which means my car is defect-free. I must go through B1, I must go through B2, and I must go through B3. So I have to take into account all 3 paths. The way you do that actually is not even called Bayes' theorem yet, but it's very much related to Bayes' theorem. The way we're going to do that, let me just write it down and explain it, okay? What we're going to do is we're going to take the probability that the car actually was built by B1, and we're going to multiply that by the probability that the car was defect-free given that it was built by B1. Okay? We're going to do that. And then we're going to add to that the probability that the car was built by B2 times the probability that the car was defect-free given that it was built by B2. Okay? And then I'm going to continue going, and I'm going to add to that the probability that the car was built by B3. And then I'm going to multiply that by the probability the car is defect-free given that it was built by B3. So this is actually the probability of event A. You're going to be using this quite a bit because most of these problems that we're going to do are going to give you a bunch of numbers. You'll have to draw a picture, and then you'll be asked, what is the probability that the car is defect-free? or whatever problem we're talking about, it'll basically be asking you, what's the probability of this end event occurring? And basically you'll just have to go through every path. You see, what this is doing is it's taking this probability of B1 is this, and it's multiplying by the probability that A has happened given that you came out of B1. So this times this. And then because it's 3 different ways to get to the end event, you must do this for every path. Plus this probability times this probability, plus this probability times this probability. Each one of these is nothing more than what we've talked about in the last section, which is conditional probability. Probability event B happens times the probability event A happened, given that we've actually gone through the other event. So that's exactly what we did last time. It's just that in these problems there are going to be multiple paths, so you have to add them up. So this is no more complicated than what we did. We're just adding up multiple paths. Okay? So before we actually do the calculation, what we're going to have is, okay, in general, if you generalize this thing, okay, what you're going to have is what's going to be called the rule of elimination. Okay, it's called the rule of elimination, I suppose, because you're eliminating paths as you go through here and taking them all into account, okay? Basically what you have is, okay, if B1, B2, B3, ... are mutually exclusive events, okay, of which one must occur And by the way, we always know that's true because there's 3 paths. The car comes out. Either he's produced by B1 or B2 or B3. These are mutually exclusive events. There's no way a car is built by both of these plants at the same time. So these events are mutually exclusive, and that's what this is talking about. The rule of elimination says if you have these events, mutually exclusive events of which one must occur, then, okay, the big giant then comes, the probability of the end event A, which is the end item event that we talked about up here before, is going to be equal to the sum from I is equal to 1 up to n, okay? And by the way, there's B sub n events, okay? That's how many paths are in this thing, okay? Okay, it's going to be the sum of the following thing. The probability of B sub I times the probability of A given that B sub I has actually occurred. Okay? And this is nothing more than what we wrote right here for 3 specific paths, basically. This is just a general form of exactly what we did before. If you look at this, this is a summation. If you haven't seen that before, basically what it means is the sigma is a shorthand way of saying that you're going to add some things up, right? So I goes from 1 to n. In this example we had 3. N was equal to 3 because we had 3 paths, okay? It's the 3 different factories, okay? So the way it goes is I is equal to 1, so you have B1 and B1 here. This is exactly what we had right here. Probability of B1 times the probability of A, given that B1 happened, plus, and then you go to the next number. I is equal to 2. Probability of B2 times the probability that A occurred, given that B2 occurred, plus, because it's a summation, I goes to 3. B3, probability of A that B3 occurred. And you stop there because there's only there's only 3 events in our specific example, okay? But this is a general thing. You could have 50 paths. You could have 50 car plants and probabilities for everything, and this would exactly rule the situation. You would just have a much longer string of things to add together. This is the general thing called the rule of elimination. Basically, all it says and all it means is that when you have multiple paths leading to an event and you know the probabilities along the paths, all you have to do is multiply the little segments together and then you add up all the branches you have. So you're doing your conditional probability just like in the last section, but you have multiple paths to get there, so you have to add all of those up because those are effectively ORed. Each path is a different way to get there, which means you basically have a bunch of ORs, so you add them all together. Okay, so getting back to our specific example, okay, the probability of A in our example is going to be equal to basically 0.6 times 0.95 plus 0.3 times 0.8 plus 0.1 times 0.65. And this is nothing more than this. This probability times this, plus this times this, plus this times this. That's exactly what we're doing. And when you write all that stuff down, the probability of event A occurring is 0.875. So if I bought a car and I have no idea where it's built, if I buy a car, given that these factories have these the percentages associated with them, the probability of having a defect-free car is 0.875. And it kind of makes sense because one of the factories has a very, very good rate of producing good cars. One of the factories is lower, and one of the factories is pretty bad. But luckily, this factory that's pretty bad actually doesn't produce very many cars. So that's why the probability is still pretty high that my car is actually going to look good. So basically, that's what these problems are going to do. Partly, that's one of the questions that they'll ask you is they'll give you all these numbers and you'll have to draw a little tree to figure out what you're doing, and then you'll have to write down the probability that the event at the end actually occurs, and this is all you're going to do. It doesn't get any more complicated than this. Okay, now this problem is a very good problem to start with because it describes exactly the tree and everything that we were interested in. Now in this example, I asked you what was the probability that the event A actually happened. Okay, and so it's pretty straightforward to multiply and add the paths together to get the event A, and you'll definitely be asked that on your test, okay? But there's another type of problem that's asked with these things. It's a little bit harder to understand at the beginning, but once you understand it, then you'll be able to have no problems with it. And that is, instead of asking you what the probability that the event A is, okay, what if I was interested in telling you the following? I know that I have a defect-free car. In other words, what if I go and I say, I bought a car, I know it's defect-free. I've driven it, it's fine, okay? But I want to know, given that the fact that it actually is behaving just fine, what is the probability that it was built by, let's say, plant number 3? I mean, I could pick whatever plant I wanted. I could say, what's the probability it was built by number 1? What was the probability it was built by number 2? What was the probability it was built by number 3? Given that the event A actually happened, which means I had a defect-free car. So you see, it's a different problem. The first problem is saying, here's a car, what's the probability it's defect-free? You can calculate that. The second one is, type of problem is, okay, I know it's defect-free. Now, tell me, what's the probability that this plant built it? And notice that all the information is here, you know, even if you don't know what the formula is, it kind of makes sense. You know how good each plant is, so to speak, what percentage of their cars are good or bad, and you know what percentage of the plants produce the cars. So it kind of feels at a gut level that you should be able to calculate what the probability that it came from B3, but this is not the kind of thing you're just going to wake up at night and say, oh, I know how to do that. You have to learn the formula here, and the thing is called Bayes' theorem. That's what we're going to learn about. Okay, so before we get there, I'm going to take you through a little bit of a sort of a derivation, a little bit, just a short one, and then I'm going to present Bayes' theorem, and then we're just going to work some more problems and apply them. Okay, so I'm going to leave this up here because we're going to use it. Basically, what we're interested in finding for this kind of problem, instead of just the probability that A has occurred, what we're actually interested in is the probability that B3 has occurred given that A has occurred. That is what we want to know. Because what we're saying in this problem is we know event A has occurred. Event A is the fact that the car is error-free. What I want to know is what is the probability the car was built by B3 given that A was occurred. That's what I want to calculate. So what we're going to do here is do a quick little derivation, write down Bayes' theorem, and we're going to find an answer. Okay? So what we're effectively wanting to know when I write it down like this is what I want to know is the probability of A intersecting with B3. When you think about it there, okay, that's what I want to know because A and B3 are the two events in question. The car was error-free, and also the fact that the B3 built it. That's really what I want. I want the intersection there. And we know from the last section from conditional probability that this is equal to the probability of A times the probability of B3 given that A occurred. This just comes from the last section and all those problems we did. Probability of A and B is equal to the probability of A times the probability of B3 given that A occurred. Okay? Now, notice we said this is what we want to find. This is the end game. This is what we want, and so this relation has that in it. So let's solve this little equation here for that. So what we're going to say is, we're going to switch colors. We're going to say probability of B3 given that A has occurred is equal to the probability of A intersected with B3 over the probability of A. All I have done is nothing more than algebra 1. I mean, you take this, you divide by A3, and so you've solved for that. That's all. That's all that's happened here. Nothing fancy. Okay. Now, the critical piece to put together to step forward and move any farther, the critical piece, two critical pieces, is that this thing down here, probability of A, we know how to calculate that for this kind of problem. We calculated that way down here with this. Okay? The probability of A, which is the end event actually happening, is just simply the series of these sums that are added together for the different branches. Each branch multiplied and inside the branch, and then you add the branches up. This is exactly what we just did just a minute ago. So we know what this denominator is. We just found this. We know this. Okay? Now, the other critical piece of information is this thing. This numerator, okay, can be written as follows. Let me write this down. I can say that this is equal to, just the top part, that this is equal to the probability of B3 times the probability of A given that B3 has occurred. Okay? Now, I just want to stop here for a second and show you what I'm doing. Just think back to basic conditional probability from the last section. Probability of A and B, this is what this means, A and B3. Can be written two ways. In general, it can always be written in two ways. You have two events that are ANDed together. There's two ways to write the answer. You can say that it's the probability of A times the probability of B, given that A occurred, or you could also write it and say that it's equal to the probability of B3 times the probability of A, given that B3 occurred. The two things are going to give you the same answer, depending on the order in which you do them. I mean, if I have two events, and I do one event first and then the next one, and I calculate the probability. If I turn it around and do the second event first and then the other event, I should get the same total probability because I have the same two events, I'm just doing them in a different order. So A and B can be written as A times B, given that A happened, or it can be written as B times A, given that B happened. It's the same thing because it's the same two events. You're just multiplying them. And you know from your experience that 3 times 4 is the same thing as 4 times 3. I mean, you can flip the order of multiplication. That's all that's happening here. Okay, you're just taking one event and you're multiplying by the other one, okay, and you can flip the order. So, given that that is true, let's continue. The probability of B3 given that A occurred, this is the probability that the car was built by plant 3 given that the car was error-free, is going to be equal to, let's write down what we know here. The probability of B3 times the probability that A occurred given B3 divided by this bottom thing. And we know what this bottom thing is. We just found that the probability that the end event happens is always going to be equal to this rule of elimination, which is just simply the sum of all of these little branches with the little individual parts multiplied together. The short way to write that is the sum, I is equal to 1 up to n, just like we wrote before, probability of B sub I times the probability of A given that B sub I has occurred. All this bottom part is you know, you have your branches like this. This thing really is just saying the probability of this times this plus the probability of this times this plus the probability of this times this, exactly like we were talking about before. Okay. So this basically is going to give us the answer. We've done it. We haven't generalized it to all of its glory of Bayes' theorem, but basically we found the answer. And the way you calculate the answer then for our specific problem, the probability of B3 given that A actually occurred, we have all the information that we now need because the probability of B3, we know what the probability of B3 is. It's 0.1. Okay? So it's 0.1 times probability of A given that B3 occurred. The probability of A, which is this one, given that B3 actually occurred, the probability of A is 0.65. Okay? Divided by this rule of elimination, which covers all of the paths. And we calculated that right here, way down here. We took, this is the top path, this is the middle path, and this is the bottom path. So we get 0.875. 0.875. Okay, so when you multiply the top and when you divide by the bottom, what you're going to get is 0.074. This is the probability that the car was built by plant 3 given that A occurred. And it's a pretty, that A is a problem-free car. And notice that this is a pretty small number. This is a pretty small probability. Let's see if we can figure out why. Event A has occurred. That means I have a defect-free car. Okay? The reason that the probability is so low that B3 actually built it, partly, is for 2 reasons. Well, the darn plant B3 doesn't make very good cars anyway because only 65% of them coming out actually are defect-free, so that's one strike against the thing being built by B3. The second thing is all of the cars being built in the USA, only 10% of them come from B3 to begin with. So those 2 things are pretty darn far against being the car being built from B3 because we know it was defect-free, but we know that that plant pretty much stinks as far as building good cars, and we know that the plant doesn't even crank out very many cars to begin with. So the probability that the thing was built by that plant is very, very low. Okay. Now there's one more thing I want to tell you here before I actually write Bayes' theorem. Now this is effectively Bayes' theorem, but I'm going to write it down in a little more, more of a fashion that you'll see in your book. Okay. What I want to point out to you is very, 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 very important because I am a firm believer in trying to understand what you're doing. If you crack a book open and you just try to apply formulas, you're going to get lost sooner or later because if you don't know what you're doing, it's like a monkey typing on a typewriter. I mean, you might type some words after a while, but it's totally luck. You have to understand what you're doing. What is this thing really telling us, okay? This, effectively, when you look at it, the numerator here, okay, this is B3 times the probability that A happened given that B3 happened. What that's saying is that's this number, probability of B3, times the probability of A happening given that B3 did. So it's this path right here. That's what we've done with the numerator. So what I'm going to write here is I'm going to say, this is just in my own shorthand words, this is the path we are interested in. Okay, this is the path we are interested in. This represents sort of the probability that we're going to get to a good car along the path we care about, which involves B3, because that's what I was trying to find out. Okay, the bottom is the probability that, let's just say it this way, that good cars are built at all, or good cars that are built at all. Okay, so basically what you're doing, because this is taking along all paths, let me write it this way, along all paths. Okay, so you see what you're doing here. You're taking a ratio. You're taking a ratio of the path we care about divided by all paths. That's basically what you're doing, right? Think about what a fraction is, right? When you say you have 1/3 of something, okay, 1/3 of something, what does it mean? You take a pie, chop it up into 3 pieces, and I give you 1 piece. That's 1/3. It represents how much of something you have when what you're talking about is less than 1, right? That's what a fraction is. This is a fraction. First and foremost, it's complicated looking, but it's basically a fraction. The top thing is basically the probability that you get a good car along the path we're interested in, along the path involving B3, because that's what I asked you. What's the probability the car came from B3? So it's the ratio of the probability that we get a good car out of the path we care about divided by the probability of all good cars. Basically the probability among all paths. So you're really taking a ratio that's looking and sort of comparing the path that we care about divided by all paths. And that ratio is basically going to tell you the relative amount that plant may have actually contributed, that plant had a chance to build that car. Okay? If this top part is very, very low, then along the path we care about, it means that plant really doesn't build very good cars. So of course the probability the car comes from that plant is going to be real low if this numerator goes very low, and so on. So I just want to make sure you understand that, because when you really look at it that way, this complicated looking formula actually makes sense. It's the path we care about along B3 divided by all paths. We're taking the ratio of these probabilities is what we're doing. Okay? So let me draw a little line, and without further ado, I'm going to go ahead and write Bayes' theorem down. Okay? Which is exactly what this is, so you're not going to see anything new. Bayes' theorem. And we're just going to kind of formalize it because this is what's going to be written in your textbook, so I'm going to teach you how to read this stuff. If B1, B2, B3, dot, 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 up to Bn, it's going to actually sound just like the other one, are mutually exclusive events, okay, of which one must occur, okay, then, what are we going to say here? The probability that, and I like to think of it in terms of plants because it's easy, the plant BR, whichever one we care about, built the car, given that good cars were built at all, given that A happened, okay, is going to be equal to the probability that BR built the car times the probability that A occurred given that BR occurred. Just let me get it down on the board and we'll make sense of it. Divided by exactly what you would think. The sum from I is equal to 1 up to n of the probability of BI times the probability of A given that BI occurred. Okay, so this is nothing more than what I just told you. It's just that this looks more complicated because, you know, if you just were presented with this, like in your book, you might look at that and say, oh my goodness, what does this mean? This is nothing more complicated than what we did. It's just that we were solving the problem specifically for plant 3. So there's a 3 here and a 3 here and a 3 here. So what you're doing is you're saying the probability that plant B, whatever, built the car given that a good car was built is going to be equal to the probability along the path we care about, B3 path. This is basically the probability that a good car was built along path B3 divided by the probability that a good car was built among all paths. So it's again taking the ratio of those probabilities along our path divided by all paths. So the ratio is going to tell me what the odds are that that particular plant built it. And if you go up here, you can see that it's exactly what this is, except instead of B3, there's little R's here, which is telling you that you can pick whichever plant. So relating it back over here, basically anytime you're confronted with Bayes' theorem, you're going to be given the fact that plant A built the car, and what you want to know is which one of, that event A means that the car was error-free or defect-free, and what you want to know is which of these plants built it. Or I may pick B2 and ask you, what's the probability B2 built it? What's the probability that B1 built it? So when I look at Bayes' theorem, even now, today, so I don't get confused, I always relate it back to this example, and that's why I presented this example first. My advice is that as we work these problems, which we're going to do here in just a minute, to do that for yourself, to go back and look, and when you see plant B1 and plant B2 or whatever, that you go back and you start thinking about how does it relate to that first problem we did. Am I talking about the end event over here, or am I talking about the intermediate events? Because it'll help you put everything together. So this is really written for any number of paths. That's why there's an R there. So there's basically all these different ways, dot, 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 all the way down to B sub R paths. As actually B sub n paths. So whichever path you pick is what you're going to put in here, and all the same end item events are over here. So every path is going to have a probability, and every path is going to be connected to A with some probability here, just like it was here. Here we had 3 paths, and the problem could have 6 paths or 10 paths or 100 paths. It doesn't really matter. It's all the same. So let's go ahead and work some problems and just get some experience with it. I think you'll find it's not that big of a deal. Okay, the first problem follows the same mold as all of these problems and goes like this. There are 3 hotels in town. 20% of your family stays at Hotel B1, 50% stay at Hotel B2, and 30% stay at Hotel B3. Furthermore, the plumbing is faulty in 5% of the rooms in Hotel B1, 4% of the rooms, the plumbing is faulty in B2, and 8% of the rooms have bad plumbing in B3. First thing we want to know is what is the probability that any given family member will get faulty plumbing? So you go to town, you know that 20% of your family stays here, 50% stay there, and the remaining 30% stay somewhere else. And we know the percentage that each hotel has bad plumbing. We just want to know if we pick a family member at random, what's the probability they're going to have bad plumbing? First thing you do with Bayes' theorem is you always draw a picture, always draw a tree, basically. So you have 3 paths in this problem, all right? you have hotel B1, you have hotel B2, and you have hotel B3. And of course, the people that stay at B1, they have a certain probability of having bad plumbing. So what we're going to say is event A is bad plumbing. Okay? And of course, all the different B1, B2, and B3, that's just the hotel you stay at. That's all it is, okay? So, what is the probability that your family stays at hotel B1? 0.2. Probability that they stay at B2 is 0.5, and 0.3 at hotel B3. Now, among the people that stay in B1, we also know that 5%, you have to convert to a decimal, 0.05, stay at that stay here have bad plumbing. And by the way, if you're going to convert percents to decimals, you just move the decimal place 2 points to the left. Okay, 4% of the plumbing is bad there, and 8% has bad plumbing in B3. So it's exactly the same problem as last time. Your family stays in this many, the percentage of people staying in hotels are split up accordingly, and each hotel has a certain probability of having bad plumbing, where the event coming out, the end item event, is bad plumbing. So that what we really want to know is what is the probability that a random person in your family has bad plumbing. What we want to know is the probability of event A happening. That's the end item event. So before we even did Bayes' theorem, the first thing we learned was the rule of elimination, which said that if you're trying to calculate the probability of the end event, you just look at all the different paths and multiply inside the paths and add the segments up. So if you're going to write that down sort of mathematically the way it was written, the sum from I is equal to 1 to n of the probability of B sub I happening times the probability of A given that B sub I has happened. This is fancy math speak. That means the probability of B times the probability of A given B has happened. And then the sub I's just mean you go for each path. That's all it means. Okay? So it's very simple math. 0.2 times 0.05, that's the first path, plus 0.5 times 0.04 plus, and along this path, 0.3, 0.08. Okay? That's exactly what it's equal to. And then when you do all this math, you get 0.01 plus 0.02 plus 0.024. And then when you add all these things up, what you'll get, the probability that a person has bad plumbing in your family, 0.054. So you see, once you know what to do, the math actually isn't hard. You just go along each path, multiplying and adding and getting the probability accordingly. Now the second problem is a little bit different. The first problem said, what's the probability of your family member, random one, having bad plumbing? The second problem, part of this problem says, what is the probability that a person that is in a room with bad plumbing was actually staying in hotel B3? It's exactly the same thing before. We know that the end event has happened. We know that this person has bad plumbing. We want to know the probability they were staying here. Okay? We want to know the probability that they were staying here. That's a formula for Bayes' theorem. When you're just given the tree and you're asked to find the probability of the end item event, you just go and you use the rule of elimination, multiply and add, and get the answer. When you know the end item is happening, but you want to find the probability that you're staying in one of these things, or that this guy led to it, basically, you have to use Bayes' theorem. So Bayes' theorem, for this problem, the probability of B3 given that A has occurred, that's what we want to know. The probability that we were actually in B3 given that A occurred. And if you just go back, you'll see it. It's exactly what we did last time. The probability of B sub 3 times the probability of A given that B sub 3 occurred, divided by exactly all the different paths. The denominator is covering all different paths. I is equal to 1 to n, the probability of B sub I times the probability of A given B sub I. So again, we're taking our path divided by all possible paths. That's what we're doing. We're taking the ratio there. So what we have here, the probability that B3 occurred is 0.3. So on the top you have 0.3. times the probability of A given that B3 occurred. Probability of A given that B3 occurred, 0.08. divided by, and this is the sum among all paths, basically giving us the total probability that the event happened, that the actual bad plumbing happened. We just calculated that right here. This is exactly what we just calculated right here. So we just put 0.054 right there. And when you do this math, what you will get is 0.44. So the probability of B3 given that A occurred is actually pretty high. It's almost 50%. It's 44%. If someone is actually having bad plumbing, the odds of it coming from B3, hotel B3, is actually pretty darn high, almost 50%. Why is that the case? Always go ask yourself that. Well, if you look back up here, first of all, hotel B3 has the highest percentage of plumbing problems. Almost double almost double the worst, which is up here. So it's very, very bad as far as the plumbing happens. Now, it has 0.3 chance of people staying there, so it's obviously not as popular as Hotel B2, but it's still pretty respectable, right? I mean, Hotel B2 is pretty popular, but it has much better plumbing. Hotel B3, pretty popular, but not the most popular. Very, very bad plumbing. So those two things together basically mean that you're going to have a pretty bad time if you actually stay in that hotel, on average, okay? So let's continue on. Let's do a couple more of these, and we'll continue to get the hang of it. The next problem says there are 4 postal delivery people in your area, and their names are John, Tom, Jeff, and Pat, okay? John delivers 20% of your mail, but loses 1 out of every 200 packages. Tom delivers 60% of your mail, but he loses 1 in 100 packages. Jeff delivers 15% of your mail, but he loses 1 in 90 packages. And Pat delivers 5% of your mail, but he loses 1 in 200. So the first thing says, I guess the question says, if you complain that your package was lost or never delivered, what is the probability that John lost it? What is the probability that John lost it? My advice is anytime you see a problem with a whole bunch of people and paths and percentages, and you can sort of see that a tree is forming, go ahead and draw your tree, and then you can figure out exactly how to solve it later, and we're going to end up using Bayes' theorem to solve it. So the first thing you want to do is always draw your picture. I always do that myself, even now, even though I know this stuff. I always draw the picture. It just helps me, okay? So you have 4 possible paths because there's 4 mail carriers, okay? So we're going to call B1 John, and we're going to call B2 Tom, and we're going to call B3 Jeff, and we're going to call B4 Pat. Okay? And the mail delivery is split up like this. John delivers 20% of the mail. Let's see, Tom delivers 60%. Jeff delivers 15%. And Pat delivers 5%. Okay? So we know the percentage that these people actually deliver the mail. Now, John loses the packages a certain amount of time, and actually so does everybody else. And we're given those probabilities, but they're not given in terms of percentages. They're not given in terms of Jeff loses 10% of the mail. It's given as follows. It says that, let's see here, it says that John delivers 20%, but loses 1 out of 100 packages. So 1 out of 200 packages. 1 out of 200 packages. That is a probability. That's the probability he loses the package, 1 out of every 200. And that comes out to 0.005. That's the number you're going to use, 0.005 in your calculations. Okay? It says Tom loses 1 in 100. So his probability is 0.001. Okay? Actually 0.01. 1 in 100 is 1%, right? Okay, Jeff loses 1 in 90, and when you do that division, that comes out to 0.011, and Pat loses again 1 in 200, which comes out to 0.005. And what we've done kind of implicitly when we wrote this down is event A is package is lost. So we know the mail carriers are split up like this. This is the percentage that each one delivers the mail, and we know their failure rate. We know the rate at which they lose the packages, okay? So what we want to know is if I complain that my package is lost, so I know event A has happened, okay? I want to know what is the probability that John, this person, actually lost it, Okay, so you know you're going to use Bayes' theorem. You know the end event is actually occurred, and I want to know what's the probability that this guy is the one that lost it. So what I want is the probability that John lost the package given that A has occurred. That's basically what I want. Okay, and using Bayes' theorem, I'm using John to kind of make it easier to understand, but you could just as easily write B1 is the probability that John occurred, the probability he delivered it, times the probability of A given that John happened. This is nothing more than Bayes' theorem, divided by all possible paths. I is equal to 1 up to n of the probability of B sub I times the probability of A given that B sub I occurred. So basically what you're doing is you're finding the probability among this path, okay, divided by the total probability among all paths, the fact that you actually have a bad package. So you're looking at what's the ratio between the bad package coming from John divided by the total probability that you get a bad package from anybody. The division of those two things is going to tell me what percentage of the time John's actually the guy doing this, which is effectively the probability that he actually delivered it. So the probability of John is 0.20, just reading right from the chart, times 0.005, that's what's on the top. And on the bottom, let me go ahead and draw this line a little bit longer. On the bottom, I'm going to have a lot of numbers. 0.20 times 0.005 plus 0.60 times 0.01. I'm just going path by path, multiplying as I go and adding, plus 0.15 times 0.011 times 0.05 times 0.005. Okay? All right, all I've done here is I've taken each path and I've gone down and multiplied each little part inside the path, right? The probability that the mail carrier delivered it times the rate that he actually fails. And we've done each path individually. And what happens here on the top is you'll get 0.001, and then when you do all of this multiplication and addition, what you'll get down here is 0.0089, and when you actually do the division, you'll get 0.11. That, my friends, is the probability that John actually tried to deliver my package given that the package was lost. Does this make sense? Well, let's go back up to our tree. We know the package was lost. The reason it's a fairly low probability is twofold. Number one, John actually does a pretty good job delivering packages. He only loses 1 out of 200. Certainly better than this person and tied with this person. So fact number one is he's actually a pretty reliable guy. Fact number two is John does not deliver the majority of the packages. Tom does. So those two things together, he does not deliver the majority of the packages. Plus, when he does deliver, he actually does a pretty good job, leads the answer to where it actually ends up, which is that John, the probability that John actually delivered this package being 0.11, pretty low for this problem. Okay, the final problem says you have 4 doctors in your area. You have Janet, Tom, Georgia, and Peter. Janet has 20% of the patients in the area. Tom has 60% of the patients in the area. Georgia has 15% of the patients, and Peter has 5% of the patients. Janet is said to be rude to 1 in 20 patients. Tom is rude to 1 in 10. Georgia is rude to 1 in 10, and Peter is rude to 1 in 20. So the question is, if you go to the doctor and you're treated rudely, what is the probability that you actually went to see Tom as a doctor? So it's a classic Bayes problem. You're giving a lot of information about multiple paths, who's rude to who, how many people go to a certain doctor, and then you're given that the end event happened that you were being rude to, and you're asked to find out what's the probability that Tom is actually the person that saw you. So what we're going to do first is go ahead and write our little table, and we have 4 paths in our tree because we have 4 doctors. B1 is Janet, and B2 is actually Tom, and B3 is, I believe, Georgia, and B4 is Peter. Okay, and we know that in this small town, 20% of the people go to Janet, 60% go to Tom, 15% go to Georgia, and 5% actually go to Peter. Okay? Now, of the people that go to these doctors, some apparently are being treated very rudely. That's what we're being told. Event A is that the patient is actually being treated rudely. Okay? So, but it's given to us in terms of sort of a 1 in type of thing. So we know that Janet is rude to 1 in 20 patients, and when you do that division, that comes out to 0.05. This is basically the probability that Janet is rude, because you know that she's rude to 1 in 20. Okay? Tom is rude to 1 in 10, which gives you 0.10. Georgia is rude to 1 in 10, same thing, 0.10. And Peter is rude to 1 in 20, which is 0.05. And we know that event A is being rude, or being treated rudely. That's what event A is. Okay, so we have doctors and rudeness. So how do we proceed? It's Bayes' theorem, obviously. So what we want to do is we want to write down. We want to know the probability that B2 has occurred given that A has occurred. Okay, given that we are being treated rudely, what's the probability that we went through this path, through the Tom path? That's what I want to know, the probability that Tom was my doctor. Okay. So going back to Bayes' theorem, it's the probability along this path, which is B2 times the probability of A given that B2 occurred, divided by the sum of the probabilities among all paths that we actually are treated rudely anyway. So it's the sum from I is equal to 1 up to n, the probability of B sub I times the probability of A given that B sub I actually occurred. And this B sub I business and the summation business is just a simple matter of adding up all the paths and multiplying within each path, okay? So now all we have to do is to do that. On the top, we're going to have probability of B2, which is 0.6, the probability that Tom was our doctor, times the probability that Tom was rude, 0.10. And on the bottom, we're going to have a bunch of stuff because we're adding up all the different paths. So we're going to have, let's go through Janet's path first, 0.2 times 0.05. Plus, of course, we have Tom's path next, 0.6 times 0.10. Okay? And then I'm actually going to run out of room, so the way I'm going to do this on the bottom is I'm going to have a big brackets here, and I'm going to say plus, going down George's path, 0.15 times 0.10 plus, and the final path, 0.05 times 0.05. Okay, so the bottom here I kind of ran out of room, so I continued. I had first path plus the second path plus the third path plus the fourth path, and inside of each path you're doing all the multiplication, basically is what you're doing. So when you do it, on the top you're going to get 0.06, and when you actually multiply all these numbers and add them all together, what you're going to get on the bottom is 0.0875, and when you do this division you're going to get 0.686. So the probability that Tom was our doctor was 0.686, very, very high, because probabilities go from 0 to 1, so this is over 50%. This is 68% chance that Tom was our doctor. Let's go and see if we can figure out why that's the case. Well, first of all, he was tied with being rude along with Georgia. I mean, there's some other doctors that are apparently nicer, but Tom was one of the worst, okay? And on top of that, Tom services a whopping 60% of everybody in the town. So those two things together, that he was one of the most rude doctors, plus 60% of the people actually come through Tom's office, means very good chance, if you were being treated rudely, 68% chance that Tom was actually your doctor. So this section covered two things, really. It covered Bayes' theorem, and it also covered the first thing that we talked about, the rule of elimination, basically. And that was basically, the rule of elimination is kind of weirdly named, in my opinion. Really what it's saying is that if you're trying to find the probability that this end event actually happened, what you're going to do is you're going to multiply the conditional probabilities along every path, and you're going to add all those up, because there's more than one way to get to the end in all of these problems, to get to this end event. And the second thing, Bayes' theorem, is the reverse. It's saying, given that A has happened, what's the probability that, pick your path, what's the probability that I went through a certain path, or through a certain doctor's office, or the probability that a certain plant built my car, whatever. It's all the same thing. And when you're doing that, you're basically taking the ratio of the probability going through your path that the end event happened, divided by the total probability of the end event happening total through all paths. So you're really taking the ratio that you're going from through one path divided by the sum of all of the paths. So you're really looking at how heavily weighted that particular path is compared to the other ones. The ratio there is going to be the chances that you actually went through that path. So with some practice, I think if you just read these problems and figure out how they're organized, you'll pretty easily identify it as needing to use Bayes' theorem. And when you do that, just label everything appropriately, label your paths appropriately, and I don't think you'll have too many problems with Bayes' theorem.